If you know the factorial, well, you'll probably know that it's a function from the natural numbers back to the natural numbers. So if I plug in a natural number, I get another natural number. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and so on. And in general, factorial is just this descending product towards 1, right? So 5 factorial is 1 times 2 times 3 times 4 times 5. Now, you've probably wondered, is there some nice way to extend the factorial from the reals to the reals? And so this function, this real function, valued at x, where if I have a natural number in it, then it's going to give me n factorial. But it's still properly defined for the rest of the real numbers. And so of course you can do this, pretty easily, right? You could just say, okay, well, at n factorial, at n, let it be n factorial, and the rest of the time let it be 0, and sure, okay, I've got a real function to real function. But that's not particularly interesting at all. We're looking for some kind of neat function that also gives us other properties. And as it turns out, this question brings about a function that's used a lot in physics and that has these really nice integral properties and that has a whole lot to do with analytic continuation and prime numbers as well. So let's look into that right now. So I'm going to sort of argue kind of unrigorously, contrarily to how I do most of the time. And this is because I kind of want to follow the argument that Euler had himself, because the gamma function kind of originates in Euler and sort of his studies on interpolation problems. So you might know about the triangular numbers and how the sum of the first n numbers is n times n plus 1 over 2. Well, you can sort of extend that formula, right, to real numbers by plugging a real instead of n. So how can you do the same thing for factorials? So Euler, he first sort of noticed, in quote-unquotes, that this product here is equal to n factorial. So this looks like a really complicated product, so let's expand it a little and see sort of why it's equal to that. So again, we're arguing very unrigorously. We're not taking any limits here. We're not trying to give a meaning to an infinite product. We're sort of just going to see that some things cancel out. So you'll notice, right, that on every consecutive terms, these 2 to the n with 2 to the n cancel out, and 3 to the n with 3 to the n cancels out. As a matter of fact, this 4 will cancel with the next 4, and the 5 will cancel with the next 5, and so on. So in general, all those will cancel out. Then here we've got 1 times 2 times 3, and so on. And as you go to infinity, that's sort of going to be like an infinite product. And then at the bottom, you've got this n plus 1 times n plus 2 times n plus 3, and so on. And so the idea is that if I take this infinite product at the top, and at the bottom I've also got this infinite product, except that you don't have the first n terms of a natural, so you don't have 1, 2, 3 all the way to n. Well, then when I take the division of the two, I'm only going to be left with the terms 1, 2, 3, 4, and so on all the way to n. So we're left only with n factorial. So again, very unrigorous argument, but as it turns out, he's not wrong. And more rigorously, we can say that the limit as m approaches infinity of this here is equal to n factorial, and you can prove this. And so in this case, this m factorial comes from these blue numbers, the m plus 1 to the n. You'll see if I take this as a finite product, then we're still left with the last numerator to the n, because it doesn't get cancelled out with the next one. So it's going to be m plus 1 to the n. And then we've got all our numbers down here being multiplied. And as it turns out, the limit as this approaches infinity is equal to n factorial. And Euler discovered, he could have stopped there, right? He could have just said, okay, well, we'll take this here. We'll take the limit as m approaches infinity of this, and we'll just plug in real numbers for n. And you can do this, and something analogous to the gamma function does come up. But he actually noticed something quite spectacular, which is if you plug in 1/2 into these products, well, in the original product, you actually get pi over 2. The way he discovered this is actually because it gives rise to a pretty well-known product of the time, I believe from John Wallis, which was known to be equal to pi over 2. And so from there, he was like, okay, well, we've got pi, and at the time, pi was really well attached to the ideas of circles and their areas, and areas are very well attached to the ideas of integrals. In Euler's time, we're still really developing how to solve integrals, and calculus is still sort of a developing field at the time. So he thought, okay, well, how about we look for some integral representation of n factorial? So the way he started is from this integral here. And so the reason he started with this integral, well, actually, the way he solved this integral was by expanding 1 minus x to the n for the binomial theorem, and I tried doing it that way, and I got something very close to the final result, but there was this one like long sum in the numerator that I just couldn't figure out how to solve. So I mean, if someone knows how Euler did it, please let me know. But I ended up just doing it by parts. So if you do this by parts here, you've got x to the a, well, you take the integral of that, you've got x to the a plus 1 over a plus 1, okay, and this part stays the same, so that's what we've got here, and we evaluate from 1 to 0, and you'll notice that if you evaluate this at 1, this goes to 0, and if you evaluate it at 0, this goes to 0, so as a whole, this whole subtraction is going to be 0. And then I add to it, well, you still got x to the a plus 1 over a plus 1, and this here is going to be n times 1 minus x to the n minus 1. Note we're adding here because usually we'd subtract, but the derivative of 1 minus x to the n is minus n times 1 minus x to the n minus 1 dx. Alright? And so this here basically gives us a reduction from starting with x to the a and going to x to the a plus 1, and the n goes down to n minus 1. We've just got this extra multiple here. So if I just keep reducing, if n is an integer, and I keep reducing until this n minus 1 becomes a 0, well then we're just going to keep multiplying by these terms at the front, each of the n's descending and the a plus 1's ascending. So that's how we get this n factorial, and we've got a plus 1 times a plus 2 all the way to a plus n, and we've got a final integral to deal with, and the final integral is pretty easily evaluated as 1 over a plus n plus 1. And so that gives us n factorial all over a plus 1 plus times a plus 2 plus and so on times a plus n plus 1. And so we've already got something that starts to resemble what we had before, but let's see how we can go a little bit further. So if we say a equals alpha over beta, right? Well, we put this substitution inside here. And so we've got x to the alpha over beta, and notice it's not a u substitution or anything because it's not the variable of integration, so we can just plug in alpha and beta into what we've got here. Okay, so it gives us this, it's basically the same product, but with alpha over beta instead of a. And now if I multiply top and bottom by beta, well, actually beta to the n plus 1, because we've got n plus 1 terms down here, so I can distribute 1 beta per parentheses, so I get alpha over beta becomes just alpha, then the 1 becomes a beta, afterwards we'd have alpha plus 2 beta, and so on. And at the end we get alpha plus beta n plus beta, and at the top we've got beta to the n plus 1, so this is the same thing. And so now I can just factor out this last one and bring it to another fraction, and I'll rewrite it a little bit as alpha plus beta times n plus 1 because it just looks neater. And so now we're left with this here multiplied by this kind of simpler product here. Okay. So now we can rewrite this because we started from the integral. So if we just divide through by the first term we had, we end up getting that n factorial over this ascending product here is equal to alpha plus beta times n plus 1 all over beta to the n plus 1 times this integral. Okay? And so now I can do some substitutions. If I do a u substitution where my new variable of integration, well, I replace x by x, well, I suppose I could say u, but I kept x here as the variable of integration. If I say x equals u to the beta over alpha plus beta, you can perform the u substitution yourself. I don't really want to explain it here, but this is what you end up getting. Basically, the x to the alpha over beta is going to disappear when you end up taking this because of the du term you end up getting, and this here just changes normally, and the front doesn't really change at all, and we end up getting this constant term being appended. And now we can rewrite this a little bit. You'll notice that the betas here partially cancel out, so we've only got a beta to the n in the denominator, and we've still got an alpha plus beta in the denominator as well. So if we write this as alpha plus beta to the n plus 1, and then we put all of this in one giant fraction to the n, then this beta to the n is going to be the same beta to the n we end up getting here, and this here is going to be an alpha plus beta to the n that's going to be at the top. So alpha plus beta to the n in the numerator divided by alpha plus beta to the n plus 1 in the denominator. That gives us alpha plus beta to the, well, just alpha plus beta in the denominator, which is what we have here. So yeah, it's a bit of jumbled rearranging things. It's just, you'll see what we're doing it. And so now comes, I guess, the most sketchy argument, which is to say, okay, well, for alpha and for beta, we're gonna, we did this for general alpha and beta, but we're just gonna plug in some specific values for alpha and beta. In particular, if I plug in 0 for beta, and I plug in 1 for alpha, well, what I end up getting is that this down here, well, 1 is alpha, 0 is beta, so I've got 1 plus 0, and so on, and this is still 1 plus 0. So at the bottom I'm going to have just 1, and at the top I'm going to have n factorial, so this just becomes n factorial, which is what we're interested in. Meanwhile, this here becomes 1 plus 0 all over 1 plus 0, so that's just going to be 1, so this whole constant disappears, and then these two are going to be 0. And so what we end up getting is sort of n factorial is equal to 1 minus x to the 0 to the n all over 0 to the n. But this is an indeterminate form because x to the 0 is 1, right? And 1 minus 1 to the n is just 0 to the n. And so you've got 0 to the n over 0 to the n, which, you have to interpret using a limit. So this is where he takes this associated limit, where he looks at 1 minus x to the h over h as h approaches 0. And you can solve this by L'Hopital's rule if you want, and you end up getting minus ln to the x. I'll leave that to you. Okay, you just take the derivative of the bottom, that's 1, and then 1 minus e to the ln x h, right? The ln x comes down, and then you're left with minus ln x as you take the limit. And so what that implies is I can, because of some limit theorems, you can just take this to the n, and that's still going to be minus ln x to the n. So that gives us a nice interpretation here for this thing here. It just means the limit as h approaches, well, we don't even have to write the limit, but if we imagine this as the limit as h approaches 0 of 1 minus x to the h over h to the n, then it's just going to be minus ln x of n. So we can replace this by minus ln x to the n. And that's what we end up getting. So the argument is quite sketchy, but this here is actually true. It's surprisingly true for a certain amount of numbers. It's not true for all the real numbers. And so now we're going to do a last substitution to get the more familiar version of the extension of the factorial, which is the gamma function, is what we're interested in. Basically, we do the substitution of t equals minus ln of x, right? And that gets us that dt equals minus 1 over x dx. And you'll note if I plug that in here, I've got minus 1 over x dx times minus x, which is going to be dx, which is what we have here. And I've just plugged in the t in place of the minus ln x. And I can change the bounds. I've got minus ln of 1, that's just minus 0, which is 0. And then ln of 0, if you take the limit towards 0 from the right, that's going to be minus infinity. And you take the negative of that, that's just infinity. And so if it's minus x here, I can take it to the front to invert the bounds. And I get t to the n. And then I can rewrite x as e to the minus t because t was minus ln of x. And so this gets us a more familiar interval. Well, might not be familiar to you, but it's quite familiar for physicists, for example, and just mathematicians in general. It's the gamma function. And it's the integral from 0 to infinity, so an improper integral of e to the minus t times t to the x minus 1. Now you might wonder why we've changed from n to n minus 1, and in this case, instead of n, I used x. Well, we're going to see why. It's because it gives us particularly nice properties to the gamma function. And so we're going to look at these properties right now. First property we want to look at is, let's look at gamma of x plus 1, okay? So if I write that using the definition we just had, that's e to the minus t times t to the x dt, okay? And I can solve this by parts. I've got minus e to the minus t to the x, so I take the integral of e to the minus t here, and I value that from infinity to 0, plus x times the integral from 0 to infinity of e to the minus t to the x minus 1 dt. And so now I've taken the derivative of t to the x in terms of t, not in terms of x. Be careful about that. Now, if you take a limit for the infinite case, you'll see that it goes to 0, and for the 0 case, it clearly goes to 0. So we're only going to be left with that second integral here. And if you'll notice, this is the standard form for the gamma function at x. So that gives us that it's equal to x times the gamma function at x. So this here is a very nice result. Gamma of x plus 1 equals x times gamma to the x. And that's for any of the x inside the domain of gamma, right? And so that already gives us kind of the, the factorial identity we want, which is that gamma of n plus 1. And I guess we already knew this from our previous definitions, but gamma of n plus 1 equals n factorial. And you can see that's just because I keep descending. This is for integers, by the way. Well, for natural numbers. If I got gamma of n plus 1, that's n times gamma of n, which was going to be n times n minus 1 times gamma of n minus 1, and so on. We go on until 0. And so this here is a very important identity, and we're going to keep that as our identity 1. Okay. Identity 2, which might seem less important, but we'll see why afterwards, is that gamma of 1 is equal to 1. And you can just solve that pretty easily. You take gamma of 1 equals integral from 0 to infinity of e to the minus t dt. You just solve that integral. So we're going to actually just solve it straight away, right? The indefinite integral is like this, and then when you take the limit with the bounds, you end up just getting 1. It's not that complicated to do. So actually, you can do it straight away. You don't even need to really take a limit, right? Minus e to the minus infinity, that's just going to be 0. Well, it tends towards 0. And, okay, well, I guess, yeah, you do have to take a limit for the upper part. And so the upper part is going to be 0, and at 0, it's going to end up being 1. You can do it for yourself. So that's our second important thing, and you can solve this by L'Hopital's, by the way. Our third one is a lot more complicated, and especially because we're going to use a result which you're probably not familiar with, called Holder's inequality, which I'm not completely familiar with either, to be honest. So what it says is that if we've got some numbers p and q, right, so that 1 over p plus 1 over q is equal to 1, and I've got two functions, ft and g of t. Forget for now what the definitions of them are. We've just taken them so that they work with our proof. Well, in general, Holder's inequality was going to tell us that the integral from 0 to infinity of ft gt dt is smaller or equal than integral of 0 to infinity of absolute of ft to the p, all of that to the 1 over p, times absolute value of gt to the q, all that to the 1 over q. Now, this is a special case of Holder's inequality. The actual theorem is a lot more general. But we're going to take just this special case. I'm not going to prove it because it's annoying to prove. So I'm just going to keep this general statement here. Now, if we look at the actual functions we took here, we picked them specifically to have this theorem to our advantage. So we'll see how. If I plug in ft and gt into here, I've got e to the minus t over p times e to the minus t over q, right? So that's minus t over p minus t over q. And since we've got that 1 over p plus 1 over q equals 1, that just ends up being e to the minus t, okay? And then the t parts, well, you're going to have x to over p plus y over q minus 1 over p minus 1 over q. So the minus 1 over p minus 1 over q is once again equal to 1. So we've only left with x over p plus y over q minus 1. And this is going to be smaller than, and when I take the power of p of this function here, well, all the p's just basically disappear. And taking power of q also just makes all the q's disappear. And note, I just kind of forgot about the absolute values, and that's because this is always positive anyways, for the domain of t that we're interested in. Okay, so now that we've got this, well, you'll note that this first part here is just the gamma function evaluated at x over p plus y over q, right? For some fixed x and y, and the p and q that we have. And that's smaller or equal to, well, this is the gamma function at x, and this is the gamma function at y. So the gamma function at x to the 1 over p times the gamma function at y to the 1 over q. So this is a nice identity in itself. And so now if I take the log of both sides, I've got the ln of this gamma function equals 1 over p times the ln of this gamma function, so gamma of x, and this is just from log properties, right? The products are going to split out into a sum, and then the powers are going to come out as a multiplication. So I've got 1 over p times the log of gamma of x plus 1 over q times the log of gamma of y. And now if I use this final identity here to get rid of the 1 over q and write it as 1 minus 1 over p, we end up getting this identity here, which might seem kind of too much, but it's actually not that hard to understand. We've got the log of gamma of x over p plus 1 minus 1 over py is smaller or equal to 1 over p times the log of gamma of x plus 1 minus 1 over p times the log of gamma of y. So sort of forget about 1 over p right now, okay? Imagine 1 over p was t. This would just be xt plus 1 minus ty. This would be t times the ln plus 1 minus t times the ln. What this is basically telling us is that the log of gamma is convex, and convexity is something you've probably seen in high school, and it tells us that it is basically graphs that look like this. So they've got they're pointing towards the top like this, right? They're concave up sometimes, you say. What it actually means rigorously is that if I take any points on the curve, right, like this, and I join a line between them, well, every point on the line is going to be bigger than every point evaluated of a function under it. So this line is bigger than everything of the function. The function's under it, under that line. And the way to do that is that, well, if this is point x, right, and this is point y, well, this is x gamma, well, not gamma, let's do this for a general function, right, x fx. This would be y fy, like this. Well, in general, this line here would just be t times fx plus 1 minus t times fy. So what that means is if I let t range from 0 to 1, then we're going to get this sort of interpolation between the y values of these two things. So from fx to fy. You'll see that when t is 0, we've exactly got fy, and when t is 1, we've exactly got fx. And so it's going to range across this length here. When I do the same inside the arguments, instead of ranging over this, I'm going to range over all the values inside, inside the curve here. So all these y values here. So what it ends up saying is that for a particular t, right, I may be here and I might be here, and I'm just saying that this value is bigger than that value. And here instead of t, we had 1 over p, but you got 1 over p from using Holder's inequality. So what we're saying is that the log of gamma of x is convex. And log-convexity is quite a powerful statement because it implies regular convexity, but it's not an if and only if direction. And as it turns out, the gamma function is so powerful, well, I'll go back here, the gamma function is so powerful that not only does it have these free properties, but as a matter of fact, these free properties, so the property that x of gamma of x is equal to gamma of x plus 1, right, that was property 1, that gamma of 1 equals 1, that was property 2, which seemed pretty underwhelming, and then finally that the log of gamma is convex. These three properties, they uniquely define gamma. And the proof of that is quite a pain, and I've gone over it before, but I didn't want to include it inside the presentation because it feels very unmotivated. But if you take these three properties, you can prove that they are going to uniquely determine our gamma. No other function actually satisfies these three properties. So that's very, very, very nice. So let's look at some other identities, including the gamma function. I already said that if you it's not if you take gamma at 1/2. Well, earlier it was that the factorial of 1/2 was pi over 2. In this case, if you take the gamma function at 1/2, you're going to get the square root of pi, which is a little analogous, but not exactly the same. You've got this nice identity here as well, and you'll note that the square root of pi here is just gamma of 1 over 2. So it kind of feels like you're kind of removing this 1 over 2 here, taking a sort of average with the 2 to the x minus 1. I think the identity just looks very neat. This here is very important as well. This is the beta function. And the beta function is described by the gamma function, and you'll see that this integral is actually of a form that we looked before, where we had x to the a times 1 minus x to the n, right? And if you conveniently rewrite it as this, we call it the gamma of a beta function, and that appears also quite a bit in physics as well. And so it has this nice relationship to the gamma function. And finally, this here is super important. This is Stirling's approximation, and I wanted to prove it at first, and I realized it might take a little bit too long, so I left it out. I left the proof out of the video. But gamma of x plus 1 is asymptotically equivalent to e to the minus x times x to the x times the square root of 2 pi x. Asymptotically equivalent means the limit of your ratio as x approaches infinity is going to be 1. So what that means is when I have very, very, very large x, it basically means that these the functions are super, super close to each other. Okay, it's sort of asymptotes according to this function. And so that gives us some nice approximations for very large gamma, and Stirling's approximation is also used to evaluate actual limits on n factorial, for example, because if you replace this for n, right, if you replace it as n factorial, then you've got the n factorial is asymptotically equivalent to this for integers n, and so that's really powerful as well. So we've got, as a matter of fact, the integral which we have that defines gamma only converges on this real interval here. So we don't actually have a function from the reals to the reals, but from the open interval from 0 to infinity to the reals. Can we actually get a function from the reals to the reals that somehow agrees with the gamma function? And even more, from the complex numbers to the complex numbers. I mean, we've talked about analytic continuation before. Would be a nice way to apply it here. As a matter of fact, we sort of can. I lied to you. I said it only exists on the real interval from 0 to infinity, but it actually exists as long as the real parts of z is bigger than 0 for z a complex number. So this integral converges for real part bigger than 0. I'm not going to show you why. And so what that means is that on the right half plane, this integral is going to converge in general. But we can do even better. If you start from this identity here, which we had, and I said it was really important, x gamma of x equals gamma of x plus 1, well, using only this identity can kind of extend the gamma function to almost all of the complex numbers. For example, if I take minus 4.2, because we didn't have negative reals before, well, I basically use this identity repeatedly to end up having it as gamma of 0.8 over minus 4.2 times minus 3.2 times minus 2.2 times minus 1.2 times minus 0.2. So you see I've just gone up by 1 every time and multiplied them. And then when I go by one final time so that finally the real part is bigger than 0, I get 0.8. And then I evaluate the gamma function there because I can do it with an integral. And I divide by all of this. And this actually extends analytically the gamma function for almost all of the complex numbers, but not quite all. It doesn't actually extend it for 0, minus 1, minus 2, minus 3, and so on. So all the negative integers, well, non-positive integers actually, they don't work under the gamma function. As a matter of fact, they still don't work, but they don't work nicely, and I'll say exactly what I mean by that. And you'll see that if I applied this for gamma of -5, for example, I get -5 times -4 times -3 times -2 times -1 times 0, and so you get this sort of weird, yeah, you get this division by 0, and it's not nice. So that's sort of why we can't actually get them there. So remember in power series video, and also sort of in my exponential video, we talked about analytic continuation. And so it was that if I had some open subset of some region, well, and I had a power series expansion for a function inside this smaller subset, and I had this big function f in the bigger region that agreed with f on that open subset, and this was an analytic continuation of f, which meant that it was the unique way to extend f to this larger subset, well, to this larger set. And so we can do this here, because notes, well, we have two interpretations. We've got the gamma function that only works when real part is bigger than 0, and we've got the gamma function that works in all complex numbers, except the negative integers that we have here. And so what that means really is that the product interpretation of the gamma function, which we just looked at using that identity, is an analytic continuation of the integral representation of the gamma function. And so these are two ways to look at the gamma function. So if I looked at it on real numbers, right, this is how it's going to look like if I don't include complex numbers. And you see that add the negative integers, we've got these asymptotes here. And you might note that the asymptotes get sharper and sharper. If you look here at this graph, this is basically telling us the absolute value of the gamma function across, this would be the real axis, and this would be the imaginary axis. This gives us the absolute value in height, right? And you see that these spikes get sharper and sharper, right? They more quickly expand towards infinity as we go down here. So what that actually means, well, is as it turns out, the gamma function doesn't just have singularities at these negative integers, it has poles of these negative integers. And poles are a very nice type of singularities. They give you a lot of nice stuff, especially with contour integration, what's known as the residue theorem. And poles are basically sort of saying that the function kind of looks like a rational function. In particular, it's called if it only has poles, it's called a meromorphic function. And a meromorphic functions on the complex plane are sort of analogs to rational functions on integers. So they have singularities, but these singularities are sort of always due by division by 0. And the sharper these become, the bigger the order of a pole becomes, right? I'm not going to go rigorously in exactly what I mean by this. And so as it turns out, if you take the function 1 over gamma, that's an entire function. What that means is that, again, it doesn't have any singularities everywhere except at its zeros. And so that again, I've already said that entire functions are kind of special functions, and so it's kind of nice to have this continuation of n factorial being so nice if I just take its reciprocal. So you also have these nice identities that I'm not going to prove. But for example, gamma of z times gamma of 1 minus z, this is called, I think it's called the inversion formula, I don't quite remember. It's equal to pi over sine pi z. And this sort of explains the poles of the negative integers. You know that sine, has sine pi z has poles at all of the integers. And sort of, if you divide by 1 minus z and use some, gamma of 1 minus z, and use some circular reasoning, then you kind of see that, okay, if z is a positive integer, right, then this here is going to be evaluated as a negative integer. So you sort of get like a 0 multiplied by a pole, so something like infinity. And as it turns out, you don't actually get a pole for gamma of z. But if this ends up being a negative integer, then this here is just a positive integer, which can be evaluated, and you still get a pole. Circular reasoning again, but that's one sort of motivation, I guess. You also have this very nice identity for the second order derivative of the log of gamma of z. Again, the log of gamma of z is very useful, and we already saw that it's convex. And it's actually just 1 over z squared plus 1 over z plus 1 squared plus ... over z plus 2 squared plus ... And it gives us sort of a nice relationship with the zeta function. The zeta function, which is so important in the Riemann hypothesis, as I've already mentioned before, and you've probably seen in popular math videos. And so the zeta function of z is actually equal to zeta of 1 minus z times gamma of 1 minus z times this whole mumbo jumbo here. So that's sort of a nice connection between the gamma function and the zeta function. And I've already said at the start that the gamma function is related to prime numbers. Well, this is because the zeta function is related to prime numbers, really. And then finally, I told you the reciprocal is entire. And so we can sort of actually factor it in terms of its zeros. And it's factor it by sort of an infinite product. So we take z to the e to the gamma of z, so small gamma, times 1 plus z e to the minus z times 1 plus z over 2 e to the minus z over 2, and so on. And you can see sort of how each of these zeros, right, correspond to the poles of gamma of z. So when z equals minus 1, right, this here becomes 0, so this whole, if I take the reciprocal of this, then we'd have a pole. When z is equal to minus 2, this would be 0, and then minus 3, minus 4, and so on. And there's an interesting thing to say about this constant here, because this is actually just a constant. It's called the Euler-Mascheroni constant. It's approximately equal to 0.57722, and you can keep expanding this decimal, but we don't actually know if it goes on forever without repetition. What I mean by that is we don't actually know if this constant is rational or irrational at all. And I think that's kind of amazing. For something to arise, and I mean, you'd really expect it to be irrational, because I mean all this stuff is kind of weird, but we still don't actually know if it's rational or irrational. There's always these stories about constants like that. I think there was this one constant which was thought to be like this really complicated number, and actually just ended up being 1 after like some research. So that's all I wanted to say about the gamma function. I hope it interested you. I hope you weren't too scared by all the integrals we looked at the start. Even if you're not very good of integration, you can just kind of follow along with the reasoning, I suppose. But I think it's nice also to see Euler's reasoning historically, even though we skipped some of his steps, to see that such a great mathematician, can start with this really unrigorous stuff, and that was generally true by Euler. That's also how he solved his Basel problem, for example. And in the end, it still ends up being true. But you see that it's not always wrong to look at mathematical problems without rigor and just kind of hand-wave things. Because a lot of times you do get right things, and if you can justify them afterwards, it's good. But as long as you get this nice motivation for what you're doing, and then you can go along with your proof, it's never wrong to do things without rigor. So, yeah, that's one thing to learn from Euler. And I'll see you in the next one.